It is my pleasure to welcome you to this course again. Today is a module 2 for this week. Last class we had seen finite volume formulation for 1D diffusion equation in detail. We understood the terminologies used in finite volume mesh control volume arrangement and how to identify distance between node and node, distance between node and control surface. Then we explain in detail diffusion equation. Then we understand with the help of an example problem the same formulation. We also try to do for near boundary node treatment. So, we took example problem and we did up to left boundary node for that problem. We also returned equation finite volume formulation for continuity equation. To recapitulate what we did, this is important to show again, understand again the terminology is used. So, here is mesh arrangement, P is a point of interest and the full circle is a node that is marked here as a P, which is a point of interest. Then for a uniform spacing, the arrangement is shown, east side capital E and west side node is capital W. Similarly, to the west of west, it is given here as a WW, to the east of east is given here as a EE. Then a control volume is constructed around the node of interest. So, in this case the full color shaded portion is a control volume and the left side surface is shown here as a W, small case w. Similarly, the east side surface is shown here as small e. Distance between node P and the face, because it is one dimensional in x direction, we say it is delta x P W. Similarly, on the other side delta x subscript P and small case letter e. Similarly, distance between nodes and node. So, here it is between node P and node W is again delta x, but with the subscript capital P and capital W. We have seen all this. We took this example problem, that is one dimensional heat diffusion equation, and for this particular problem we say source term is 0, it is very simple, and this is the illustration required for the problem, and the cross section is circular and area is given as 0.0001 meter square. The left boundary, which is referred here as A, and temperature at that boundary is given as 100 degree Kelvin. Similarly, the right boundary, which is referred here as B, and temperature at that boundary is 400 Kelvin. The distance between left boundary and right boundary is given as 1 meter. We said okay, we will divide the region into 5 equal control volumes. So, we have 1, 2, 3, 4, 5, and we understood all the distance between node 2 to node 1, node 2 to node 3, because it is a equal spacing, it is referred as delta x for all the nodes in between nodes, and for the node 1 and node 5 which are near the boundary, because it is equal spacing, we have delta x by 2 as a distance between node and the boundary. So, in this case distance between node 1 and the left boundary is delta x by 2. So, we identify 2, 3, 4 nodes are internal nodes, 1 and 5 are boundary nodes. We have the discretized form of the governing equation as previously derived, and in this case there is no source term and that particular term is not there, and again in this case k, that is a coefficient, is constant and delta x is also same value. We also identify terms in the coefficient for T p has same term as coefficient for T w and T e. So, this first term corresponds to coefficient for T at east node. Similarly, the second term here corresponds to coefficient for temperature at west node. So, the T p coefficient of T p is a summation of these two coefficients, and that is how we write as A p T p equal to A e T e plus A w and T w with coefficients written as shown here. And we say P is a node of interest, it runs from left to right. In this case, we initially consider only internal nodes. So, P will actually run for node 2, 3 and 4, and we are able to evaluate corresponding values k by delta x and A. For node 1, the left side is boundary referred here as A, and temperature is given as a boundary condition. For node 1, right side, that is east, is available. Hence, for node 1, this is written separately K A T e minus T p by delta x, whereas on the other side it is boundary condition T p minus T a, which is the boundary condition, and the distance is delta x by 2. Now, we will also try to do similarly for other node. Before that, we will identify that T p is a node of interest appearing in term here as well as in the term here. So, we collect these coefficients. So, k by delta x A, 2 k by delta x A, T p equal to terms on right hand side. 2 k by delta x A and T a is considered as a source term, S u plus S p T p. S u is 2 k by delta x A into T a, and S p is minus 2 k delta x into A, right. So, if you extend this procedure for the other node, in this case 5, node 5 is a node next to the right boundary, and K A T b is coming from right boundary minus T p by delta x by 2. Again for node 5, west side, that is 4 is available. So, we write full term T p minus T w by delta x equal to 0. Again we identify T p, it is a point of interest appearing in both these terms, collect corresponding coefficients. So, you are able to rewrite that equation in this form, k by delta x into A plus 2 k by delta x, 2 is coming because of this delta x by 2 into T p equal to k by delta x A T w plus 2 k x by A, 2 k by delta x into A multiplying temperature at B. So, we have full discretized form for each node. Now, we have done all this without actually substituting number. In particular example problem that we have taken, k is defined, A is also known, and delta x depending on the mesh that you have considered. In this case, we have considered 5 nodal points, 1 meter is the distance. So, delta x becomes 0.2. We can substitute those values and evaluate the constants. So, K a by delta x is one such value, happens to be 100. Okay. If you substitute this 100, which is K a by delta x, in the discretized equation for all the nodes, node 1 to 5, then corresponding coefficients are evaluated and they are all tabulated here. Let us try to understand this table. The first column is for node 2, 3, 4 are internal nodes. Full discretized equation is available, hence 2, 3, 4 can be evaluated and you get these coefficient values evaluated as shown here. And we also learned in the problem statement there is no source term, hence that external source term are all 0 here. Okay. Now, for the node 1, the left boundary is there, but there is no west node, hence the coefficient A w is actually 0. whereas east node is available and you are able to evaluate east coefficient for the node 1. And similarly, for node 5 there is no east node, the east surface is the boundary condition location itself. Hence, AE is 0 and AW you are able to evaluate. The boundary conditions which are enforced appears as a source term and they appear for corresponding node 1 as shown here and for node 5 as shown here. While writing the discretized equation, we also observed that point of interest coefficient, that is AP, is a summation of neighboring nodes coefficient. So, in this case AP is equal to AW plus AE and then source term. Of course, in this case source term is not there, it is 0 and we get here this AE plus AW is evaluated as shown here, right. So, for example, 100 plus 100 equal to 200, you are also able to cross check, right. Now, this minus SP is 200 here and that is added to 100, you get 300 here. So, if you write this if you write this set of linear equation in the form of a matrix, then you will get a matrix and you can get a structure like this, right. So, this is the T1, T2, T3, T4, T5 are the values to be determined and this is what is known as a column vector of unknown value to be determined. And to the left of it is a coefficient matrix. This corresponds to, each row corresponds to one particular variable in this column vector. And the right hand side there is another column matrix and that is a known value. So, in this case, for example, temperature at A is coming from boundary condition, temperature at B is coming from boundary condition, hence it is a known value. If you look at this matrix structure, you observe along the diagonal. So, the values are here, for example, 300, 200, 200, 200, 300. This is main diagonal. Then you have one diagonal following the diagonal just above, that is called super diagonal. So, in this case it is minus 100, minus 100, minus 100, minus 100. Similarly, there is one diagonal immediately following the main diagonal just below minus 100 and so on. So, you get a structure what is known as a tri-diagonal matrix. So, one main diagonal, immediate super diagonal and immediate subdiagonal. We have already seen different matrix structure in last week class, pentadiagonal of two different forms, tri-diagonal and only diagonal matrix. Okay. There is a separate procedure available how to invert this matrix. We will reserve the discussion for next week class. Okay. So, in this case, if you happen to invert this matrix, then you determine these values of T1 to T5. Above tri-diagonal system of equation is solved to find the values at nodal points and it so happen values are determined and it is given here T1 to T5 in this form. And for this simple problem, analytical method of getting the solution is possible and that is what is referred as exact solution. Because it is a simple problem without any source term, it happens to be a linear distribution as temperature is equal to 800 x plus 100 and this runs from left side to the right side. You can substitute value of x depending on your computational node and get exact solution at the computational node and compare with your computed CFD computed results. It so happen in this case they are almost the same. Okay. So, numerical solution obtained is same as exact solution. It is a very simple problem, hence it is not a surprise that they both match. Later we will see there are situations where exact solution is not matched. So, what we have done in the example problem is without source term. So, you can try this problem with the source term. In this case the figure is shown, Lx is the length because it is 1D, it is in x direction, and there is a temperature distribution from one side to the other side, k value is given, length is given. In addition, there is a heat generation source term, value is given as 1500 K, that is kilowatt per meter cube. Then though it is shown as a 3D, that is dimension in y direction as well as in z direction, they are so large that temperature variation along the y direction and z direction can be neglected. Hence, the problem is 1D. To solve this problem by diffusion method, that procedure explained for a diffusion equation with the different mesh size. Okay. The last problem we had explained only with 5 nodal points. So, in this case you can try starting with the 5, but again try with 8 and 20 what is happening, and there is again analytical solution available for this problem, and that is also given here, and compare this. We have seen so far one dimensional diffusion equation, and we got explanation with the help of an example. We will now extend for 2 dimensional. Now, in the case of 2 dimensional, governing equation becomes dou by dou x of gamma dou phi by dou x plus dou by dou y of gamma dou phi by dou y plus s equal to 0, and the mesh or the finite volume is shown here. In the case of 1D, it was only east and west, now we have north as well as south. So, let us look at this figure in detail. So, P is a point of interest or node of interest, and you construct a control volume around that node of interest. Now, in 2 dimension, so you have a delta y as well as delta x defining the size of the control volume. To the node of interest P, on the right side you have a east node, on the left side you have a west node. In addition, you have one node on the north and one node on the south. As we did in 1D, we also have to define control phases. So, this phase we already learned is marked as W with a letter small letter case, and east side is marked with the letter case E with small case. In 2D, we have 2 more phase, one on the north, and that is shown here small case letter N. Similarly, on the south you have one more phase which is marked with the letter S, small case letter S. Now that we have described control volume and terminologies for the 2 dimensional situation, let us now go to the procedure of getting the discretized equation for 2 dimensional equation. When you integrate the governing equation over the control volume, and that is what is shown here. Let us now do the first term, that is derivative in the x direction. For the sake of simplicity, you consider uniform grid delta y equal to delta x. So, the first term is gamma a dou phi by dou x evaluated at the east face minus gamma a dou phi by dou x evaluated at the west face plus gamma a dou phi by dou y evaluated at the north face minus gamma a dou phi by dou y evaluated at the south face. Now, when you compare what we did for the 1 dimensional case, we have now 2 additional term for the second direction plus source term S bar delta V equal to 0. We rewrite that equation again here. Now, we need to evaluate dou phi by dou x at east face, west face. Similarly, dou phi by dou y at north face and south face. For that sake, we reproduce the finite volume terminology as shown here. Now, we have already done evaluation of fluxes at east face and west face in one dimension, and that is what is shown here. So, gamma E A E phi at east node minus phi at p node divided by delta x p e minus gamma w A w phi at p minus phi at w by delta x distance between node of interest p and west node. We now have two more terms corresponding to y direction, and they are shown here, that is gamma n A n phi at north node minus phi at p node divided by delta y, that is a distance between p node and north node. Similarly, the other term, that is gamma s A s phi at p node minus pi at s divided by delta y p s, and source term is evaluated as we did in the one dimensional case, that is S u plus S p phi p equal to 0. The same discretized equation is shown once again here. Now, we need to rearrange as we did in one dimensional case. The point of interest term, that is phi at p, appears in all the terms. So, we rearrange, we collect coefficients multiplying phi at p. So, when we rearrange the above equation, we get final equation as shown here. So, this equation on the left hand side has coefficients multiplying phi at p equal to all other terms on the right side. If you look at this equation, left hand side is unknown, right hand side is contribution from neighboring nodes. In the case of two dimensional case, neighboring nodes are west node, east node, north node and south node. Let us rearrange the coefficient as we did one dimensional case in the form of a standard expression, that is A e A w. Now, we have A n and A s also included. So, you can immediately recognize A e is gamma e by delta x p e A e, then A w is gamma w delta x p w A w, gamma n by delta y p n A n is for A n, gamma s by delta y p s A s is for A s. The node of interest coefficient A p has contribution from neighboring nodes, that is why it is written here as A w plus A e plus A n plus A s plus source term. So, the final discretized equation becomes A p pi p equal to A e phi e plus A w phi w plus A n phi n plus A s phi s. Now, in 3D it will have one more term added in the governing equation corresponding to third direction, that is z direction. So, the term new term is dou phi dou z of gamma dou phi by dou z and source term equal to 0. So, in 1D it is just element, in 2D it becomes a area, in 3D it becomes a volume, and that is a sketch, and this is the control volume. What is shown for a simple case, a cube, and all these dashed lines corresponds to that cube representation, and the coordinate is also shown here x, y, z. So, in x direction you have along the x direction east node, capital E east node and west node, and this is the point of interest P, right. Now, along the y direction you have a north node and south node. Similarly, along z direction you have a top T and bottom B this surface and node capital T and bottom node capital B. So, for all the surface, the center of the surface is actually marked here, and that actually corresponds to particular surface. So, for example, small case letter T is a center point for this particular top face. Okay. Similarly, the B is marked, small case letter B is marked as a center point for this particular bottom face, and so on for other surface. Once again, this is for simple situation, a cube is taken, hence it is very simple, all sides are equal and center is able to fix. Imagine how will you do for unstructured mesh. So, procedure is the same as we did for 1D and 2D. As we did in the case of 1D as well as 2D, we identify control surface and all the derivatives required at control surface are evaluated based on function values at the respective nodes. So, you observe here two new term, one corresponds to top, another one corresponds to bottom, and we observe here the derivative phi t minus phi p by delta z p t, the distance between nodes p and node t, and this will give dou phi by dou z. Similarly, for bottom, okay, and source term is there. Again, you identify that node p, which is a point of interest appearing in all the terms, So, we collect all terms where phi p is there and put them together, and you get a coefficient for phi p. This is a node of interest, or in other words it is unknown. So, we retain on the left side, all other terms are brought to the right side. So, we get phi w phi e as we had seen in 1D, additional term north and south as we had seen in 2D. Now, two additional term phi t and phi p for 3D. Similar observation, terms inside coefficient for node phi p are nothing but terms for each neighboring node. So, for example, the first term gamma e by delta x p e a e is coming from gamma e by delta x p e a e for node at E, and you can observe that similar for other neighboring nodes. So, this becomes a summation of individual neighboring node contribution plus the source term. So, similar pattern we will follow A E, A W, A N, A S, now A T and A B. These are coefficients rewritten, and A P is a coefficient for P node, and as observed before, it is summation of all neighboring nodes coefficient. So, final discretized equation becomes A P phi P equal to A E phi E plus A W phi W plus A N phi N plus A S phi S plus A T phi T plus A B phi P. Source term is not there, source term is already included in phi P. Okay. Now, you can imagine how it will be while writing code or solving a 3D problem. We have so many coefficients to be evaluated, and we will see how to handle with ease in future classes. With this, I will come to end of this class. Thank you.